Good afternoon, everyone. Looks like most folk are back in. The quick question there about using SPAC to manage the oneAPI. Yeah, some folk from Intel have been working on packaging it. So to my knowledge, it all works. I haven't tested it personally. We've been maintaining some installations on some other HPC systems. They, as far as I'm aware, don't tend to use, or the ones that we're on at least don't use SPAC. So I haven't been able to tangle with it myself, but it seems like it's. Oh, this is installed in server. Okay, cool, awesome. I mean, if that's true and that worked, then fantastic. That'd be amazing. It's certainly much easier. I guess we can just think about getting going on the afternoon stuff. So our next section is going to be in error handling and then data parallelism, and we've got small samples for both of those. So we'll aim at both of these now. I guess I can close these tabs. I will just find the files. Okay. Oh, and then I need to share a screen because I stopped doing that. I forgot. Okay, right, I'll do that just now. I'm glad that I checked. Otherwise, I've just been blithely talking away while you guys couldn't see anything. So okay, it looks like it's showing for me. Hopefully it is for you guys as well. I guess we'll get going. So yeah, obviously these sites we want to learn how does the SYCL API tell you about and how do you handle errors from it. We'll learn about the difference between synchronous and asynchronous exceptions. We'll learn how to handle those and then get further information about the error. And the stuff about the host device we're not going to cover because that is not in SYCL anymore, but it's still part of the sites. So this is sometimes a sticking point, I guess, but in SYCL, errors are all handled by throwing exceptions, not least because, there's a lot of the API is, C++ object construction, so it ends up, looking a lot like that anyway, particularly if something happens when you try to make an object or whatever. And yes, you should handle errors. The thing that is different in SYCL, I suppose, is that there are two kinds of errors: synchronous errors and asynchronous errors. They happen in different parts of the SYCL runtime. And synchronous errors, you will have seen before, they are exceptions that are going to be raised by like the actual user threads. So you could try to construct. I suppose, for example, you might try to construct a device and you've required that it has certain aspects. If that device isn't available on your system, you get an exception, and that's how we return errors from ordinary object construction. The asynchronous errors are different, and we'll go into the differences now. So the reason for this difference is because the kernels are asynchronous and will throw asynchronous errors. Everything else happens on the host and will throw normal synchronous ones, and you can see the kind of decoration, or well, the comments here indicating what is which pieces of the code run where. And effectively, this means that everything that happens inside the SYCL interface is kind of synchronous, and then like everything that happens asynchronously to the user, stuff that happens in the runtime, stuff that happens through the backend, tends to come through an asynchronous exception. In older versions of SYCL, if you didn't handle an asynchronous error that happened as a result of like your code running or whatever, then your application would actually just kind of blindly keep going. The SYCL 2020 has added a so-called asynchronous handler that if you don't override it with your own one, then it will call terminate and stop the application. So that's probably a safer default. It's definitely good for development, because when something goes wrong, you'll see about it pretty much immediately. So yeah. So yeah, typically API functions in SYCL will will throw exceptions. Sorry. Therefore, you have to wrap your code in a try-catch to see which bits, if any, have thrown an exception, have gone wrong. So the the other half, as I mentioned before, is that the queues on construction. Looks like the formatting has gone a little bit funny on this one, but yeah, anything that happens after the command group has been submitted to the queue will be asynchronous, and you have to pass in some kind of asynchronous handler, and we'll cover exactly what that should look like. In order for things to be passed to this asynchronous handler, you also have to call this function throw asynchronous, or there's also one called wait and throw. It won't do it until you essentially tell it to, because it needs to have a point where you give control to the runtime to allow it to pass those exceptions from the scheduler onto the user thread, essentially. An asynchronous handler is another C++ Lambda or function object. We're lousy with them. And it has this single argument, which is an exception list. The exception list is basically just a bunch of these exception pointers, and exception pointers is an STD exception pointer. And the thing that you can do with those is you can rethrow them. And when you do rethrow them, then it goes into the normal handling thing. So you can see here, this will throw the exception from the list. So here, the standard thing to do is to say like, what was the error? You've got exception, what's happened? And there'll be some, implementation specific string indicating what it thinks has gone wrong. There are some differences here between SYCL 1.2.1 and SYCL 2020. The samples should have been updated for this, if I remember correctly. But you can query using this free function, error category 4, which will allow you to correlate an error code that you get with the exact, it will tell you what that corresponds to for the backend that you're running on. And this is because, the different backends will have some kind of error code coming out of them. And you don't know what that necessarily means, because error 5 for OpenCL might not mean the same thing as error 5 for CUDA or something similar. So this kind of allows you to paper over these differences and work out what it is. There are some queries that you can now do on the exception. Again, this is kind of newer code added by SYCL 2020, where you can check for the error having a context associated with it, and then that would allow you to check that, for example, where did the error come from? So this one here would allow you to say, like, right, I know that it was actually associated with specifically this queue because I've checked the context, and I'm going to do this specific error handling. So there are ways of like you can do things like that to further identify what's gone wrong and use that to try to recover from the error situation. There are a few different types of exception. We have different kinds of, we unified them in SYCL 2020, and now they just have different error codes associated with them. So it could be like error code runtime or error code kernel that again will tell you where or what roughly has gone wrong, and perhaps would allow you to categorize that form of error in and do the correct kind of handling in your application code. So the last section here is about debugging SYCL kernel functions. It tells you to use the host device. That said, the aspect host debuggable in SYCL 20 is what potentially allows you to debug this. And so the actual concrete example, again, previously we'd mentioned that the CodePlay is working on the native CPU implementation, which is inherently debuggable. It's just normal CPU code, normal assembly. And similarly, the OpenCL CPU backend that Intel distributes with oneAPI can be used to debug kernel code as well. And you simply just set your breakpoints in GDB as normal. CUDA, I believe, has a good debugging experience with CUDA GDB. I think HIP has a similar, is it Rock GDB or something? I think I've had worse experiences with that. But those both also allow you to debug GPU code. So it is kind of like something you can do. But if you want the sort of normal familiarity of a CPU debugger, then there are options available for that. If not the host implementation that 1.2.1 has, then some kind of CPU implementation would allow for that. This is how you would query. This is how you would select something. So this aspects are, I guess you could call them features or well, the problem is aspect is actually just the best word for it, and that's what they used. And this allows you to say, like, I want to select a device which matches this list of aspects. And so here we can say, yep, I want to be able to debug it on the host. That will probably return some kind of CPU device, be it native CPU or the OpenCL CPU. So this one is a fairly short sort of section on error handling. I suppose it depends how familiar you are with exception handling in C++ generally. If you have any particular questions about that, please let me know now. Otherwise, we'll open up the next code exercise. Well, I'll open up that now, but I'll listen out for questions if you have any. Okay, so the task here is to catch both synchronous and asynchronous exceptions. It can be quite difficult to force exceptions to happen in SYCL. Sometimes it is designed for the most part so that you can write code fairly safely, I would say, or at least this is partly a goal of the API. However, this one kind of sets up at least one problem, which is the buffer was given a range 1 and now we're accessing 2 elements of it. So that is going to be a problem. It might be possible to make something go wrong with executing by trying to read device memory that you don't have access to, but it's normally fairly difficult to do something like that. So as the README says here, add in a try catch, see if you can catch the exceptions as they happen, and see if you can do something or like catch the errors that are, sorry, the exceptions that are being thrown as a result of the stuff like accessing beyond the range of the buffer. And if you have any questions of that, please let me know. How's everyone getting on? Has anyone managed to throw where the buffer access seems to check for out of bounds and every access doesn't occur penalty practice? Does it? Is that maybe the host implementation?
I think here in this example, we're just constructing the accessor and not accessing the data yet. So it's on construction, definitely checking it. I'm not sure about the actual data access. I think it's not checking.
One of our colleagues definitely added a mode to Compute CVP, which had like an out of bounds access checker thing, and it would tell you which thread accessed out of bounds and stuff. You had to opt into that, like it wasn't a default mode of operation. Okay, right, cool. I've been interested in this recently. I think there is a lot of evidence that suggests that there is not much performance penalty associated with bounds checking containers normally, but I think that's true on CPUs. I think on GPUs it's going to get a bit weird. And again, it's very difficult to like return that information to the user. So I don't know, but certainly for CPU, I think I would say it's fairly cost neutral. That, and I'm sort of fairly interested myself in like trying to tell the compiler that it statically knows that the bounds check isn't needed in some circumstances, like using like for each loops, over normal for loops is going to give you guarantees that it just doesn't need to do it. So yeah, you also have to use language expressions, queue submissions, error handlers, etc. You can use function objects instead, but actually you can also use bind expressions if you want to be, if you want to go back to the very old way of doing it. I guess probably what you're really asking is, can I use like a free function? And the answer there is no. Oh, huh. You might be able to use like std function or a function pointer for the error handler. I have never tried, but there's nothing from an implementation feasibility point of view that says that you couldn't. The restriction on the kernel is still there, but you might be able to use just like a function pointer or something for the error handler. How do you feel about Freddy's now code only reporting the first exception in the list? Yes, good spot. Realistically, you would have to have your error handler either throw it somewhere else or have a try catch in that loop and then handle it. Yeah, that is true. I think it's possible that, I guess there is this notion when we were doing this that you might end up in a situation where you had a couple of different errors stemming from a couple of different kernels and you only check at the end. I think realistically, most of the time, you have like one error because something went wrong, or your entire application is hosed because the device has like been disconnected or something. That's my general experience. Most error handlers I've written have never been run. Is really the thing. So definitely a good point the way it's written is that it will only ever catch the first exception. That it tends to be a list of one exception, if any at all. I think about this one, and I think sometimes I wonder if we could improve the spec on it. But I've never. Well, it's been 10 years and no one's come up with better ideas yet. So that said, patches are welcome, and if you have better ideas, then the community would be really interested to hear them, I'm sure.
Yeah, I guess this also depends on the use case. I think in scientific HPC fields, as soon as you get one error in your application, you can't really be sure about the outcomes of your computation. So you would need to fix the issue and start again anyway. Whereas in embedded programming and some devices that run somewhere on the edge or in cars and things like that, there, of course, you can't start again. You have to continue. So you have to be able to deal with all the errors during the runtime and then continue cleanly.
Over lunch, I was actually messaging one of Raval and myself's colleagues who is working on the safety critical SYCL efforts, and it's always interesting talking to him, but we've previously had discussions internally about error handling and so on, because obviously the car doesn't get to say, oh, there was an error, I'm exiting, good luck. So, there's definitely a lot of discussions about what that will end up looking like in the future. If you, since you've heard exceptions, oh, those were the structured ones, right? Where you could only catch them in a certain place or something? Is that it? There was definitely, yeah. I never looked closely enough at those, but they did sound interesting for like a slightly more focused, I suppose, error handling rather than just, throw exception, end up anywhere. Yes. I guess the intent behind why this was written the way it was to unify all the error handling into one path, which I think isn't a bad goal. I think it makes sense to say, well, we want to keep our error handling for our application in one place, and we want all our error handling to go there. And this is a way of like enabling that. But ultimately, maybe that's just not what GPU programming looks like. Or maybe we should be reporting the errors asynchronously and then giving the user tools to turn those into exceptions that they can then throw back up the stack. Which I suppose is kind of true, because you can take the exception pointers yourself and do whatever you want with them. Like, it doesn't, you can do what you like. But certainly the way that the default stuff is all written is kind of, well, throw one and then who knows what will happen. The rest of them get lost. So.
I mean, it's worth pointing out that the default behavior of SYCL is still much nicer than the default behavior on the lower level APIs like CUDA, HIP, oneMKL, where you just get an integer error code returned, and if you do not anything with it, then it just continues.
That's true. That is very true. The inherit from std exception. Runtime is in the slides. I'm going to double check before I say anything else. I'm sure it said.
The specification says it inherits from std exception.
Okay, but not like runtime error or anything specifically.
No, specifically says in the class definition in the spec.
Gotcha. So has anyone managed to get this running or not running? I guess, yeah, this is one where we want to see the errors. Which is a bit different. You have the error you want. Fantastic. Yeah, it's kind of hard to make the kernel reliably fail. But you can make kernels that will do something silly, like massively run off the end of an array, and ideally the GPU runtime will catch that. So yeah, great stuff. All right, fantastic, guys, well done. So that's that. I've got too many windows open. The next lesson that we'll be moving on to is the data parallelism one. So this is where things get kind of interesting, and we do some actual, excuse me, we do some actual talking about the kind of how to run a massively parallel kernel or whatever. So let's just find that now. Okay, so in this one, we're going to learn about task parallelism and data parallelism. We will talk about the SPMD, which I think is single program multiple data model for describing data parallelism. We will learn about the SYCL execution and memory models, and then learn about, finally, how to enqueue functions with parallel for. Up until now, we've been using the single task. Subsequently, we're going to use the parallel for. So we envision the difference between task and data parallelism as something of a gradient, but at the far extremes, task parallelism would have several potentially distinct tasks executing in parallelism, whereas data parallelism is the same task, which is always performed on multiple elements of data at once. And, it mentions here about latency and throughput. That's kind of generally true, but yeah, I think I could agree with that and say, yeah. Certainly, when we do GPU programming, we're definitely optimizing for throughput. And particularly these days, many processors, I think literally like every CPU you can buy, outside of quite niche embedded purposes, is a vector processor of some kind, so they can naturally do some amount of data parallelism. CPUs have these SIMD instructions, which do the same instruction on multiple elements of data at once. So you may have used SSE or more recently things like AVX 512 or whatever, like the very long advanced vector extensions. And GPUs in here inherently are designed to be parallel executors, essentially. So we can contrast here, say two implementations of a function calc, which would take some arrays, and the sort of normal sequential, and also for all of you who have done CUDA before a bit, I'm sorry. Let me know if it is too slow. The iterations are all run by the same single thread in a loop, and so there's, for argument's sake, 1024 elements. We iterate from 0 to 1023, squaring these and storing it out, and we invoke it just one time. Contrast this with a sort of parallel version where we have the input and output arrays, but we also have this notion of like an ID, which an index identifying where you exist, like what your number is with all out of the entire iteration space. And now we've essentially removed the loop construct from within the function that exists now outside of it, and we could imagine this parallel for function which runs the function calc on in and out, and importantly has 1024 total instantiations. And now this code, instead of iterating over I and accessing the ith element, each one will only access one element, which will be the one at position ID. And we would imagine running this in parallel at the same time on multiple different processors. Or processing elements, I suppose I should say. I will try to remember to, in this section, kind of talk about the equivalent CUDA nomenclature. I don't always remember it 100%. If you've ever looked at OpenCL, the naming is incredibly similar, OpenCL being a Khronos specification as well. So it took a lot of the language from that. I'm afraid, as I said, I don't always remember exactly what the CUDA naming for these things is. So in SYCL, our kernel functions are executed in parallel by work items. And you can think of each individual work item as like a thread of execution. Each work item will execute the kernel function from start to finish. And work items can run on like CPU threads, lanes in the CMD, its instruction, GPU threads, or really any other kind of processing element. Thinking here about DSPs and FPGAs, any sort of thing that is an executor can be a work item, essentially. Work items have there is a hierarchy here, essentially, and work items are run as part of a work group. The size of work groups is device specific, and there is some sort of optimal number for that. But you can choose one, and like a sort of size of like a power of 2, like 32 or 64 or something is a fairly common choice. The size of the work group can actually be affected by the resources that are used by each work item. We might imagine some small shared memory close to the processing elements. The more shared memory that each processing element uses by itself, the fewer work items you'll be able to have running at the same time, or even actually just down to the number of registers that your kernel uses. So there are different, there are lots of potential factors that can affect it. The diagram here shows that there are multiple work items within one single work group. In SYCL, kernels are executed over an ND range, and an ND range has a number of work groups and then a number of work items. Every work group will have the same number of work items. That's a restriction that comes from, back in the day, OpenCL. As of OpenCL 2, I think it was sort of lifted slightly in the sense that the last work group that you execute could have a completely different number of work items, and that would be, if you had, say, 10,030 threads instead of 10,000 1030 instead of 1024, you could have like 6 in your last group or something like that. And ARM actually ARM has an extension to OpenSale 1.2 that does the same thing. You can also just do that manually. You know, like you can, yeah. There are ways that you can code around it so that you make sure that you've always got a nice number of threads. Anyway, this is the way that you launch it is by specifying a number of work groups, and this diagram has 8 work groups, and each work group has 4 work items in it. Therefore, we're going to have the 32 total threads inside our ND range. And obviously, real code is going to range up to the thousands for something like this. If you contrast this to the CUDA model, before I forget, then you have a grid of blocks, I think is the terminology. SYCL says, here's my total number of work groups, and here's my threads per work group. Whereas CUDA, I think, says, here's my total threads count, and here's my work group size. I believe that's correct.
That's not correct.
Oh, right.
It's the same. You say I have a grid of blocks, and each block has a certain number of threads. So in this case, you would have your grid would be 4 by 2, and your block would be 4 by 1.
So in that case, I got it wrong around.
Yeah.
Oh, right. Yeah, Rafael's sake.
Work group is the equivalent of CUDA thread block, and the ND range is the equivalent of the grid.
Yes, listen to Rafael, not me. They don't let me program in SYCL anymore. Can both items and groups be ND? The ND range consists of 2 ranges, one for the items, one for the groups. That'll be more clear when we actually look at the code, I promise.
And both can be up to 3 dimensions.
Yes. Oh, right. Now I see what you mean. Yeah, I suppose confusingly, a range can, a SYCL range can be 1, 2, or 3 dimensional. Yeah. Is there an equivalent of a warp? Yes and no. SYCL 2020 introduced subgroups. You would expect that a subgroup would very naturally correspond to a warp, but things like warps are a hardware detail, so SYCL doesn't fully expose those because it doesn't know what hardware you're running on. But subgroups, I would say, tend naturally to match very well with that. What's a wavefront? So yeah, like you could choose like a subgroup size of 32 on Nvidia or 64 on AMD, because I think that's their wavefront size, and that can produce very, very, very high performance if you end up doing something like that. We don't cover subgroups in this, but there's other documentation out there. Cool. Right, that's not it. Yeah, okay. So yeah, the ND range describes this iteration space, how the work items and work groups are composed together. As Rafael was saying just there, it can be in 1, 2, or 3 dimensions. And the global range describes the total number of work items that you'll have in each dimension that you want. And the local range tells you how many there will be in a work group. So these numbers have to divide each other nicely. And you can see here that we have an ND range, I think with CTAD and implicit conversions. I think this is almost compiled with just the curly braces of this, but I don't remember. Or at least, sorry, my former boss years ago, I remember, was really pushing to have this in the spec. And I think some people disagreed with him, but he was like, no, we should just make it nice and easy. He wanted to do less typing. So I think this can almost work as is. But it's saying, this is a 12 by 12 grid, and I want 4 by 4 threads in each of the work groups, and therefore, when you divide them out, we have 9 total work groups, 3 in each dimension.
Yeah, and there's an important distinction here to CUDA, that here the global range, it's the grid size times the block size. So it is it must be divisible by the work group size.
Yes, that's one of the ways to get synchronous error, is to make your range, your submission range, not divisible properly. That's one of the ways. Yes, so the SYCL execution model says that multiple ARC items will generally execute concurrently, and we would expect that on some kind of vector hardware, this will be done in lockstep. It means that the same hardware instructions will all be executing at the sort of same point. The number of work items that can actually execute at the same time will vary from one device to another. That would be, you know, like the number of what do you call them, execution units on Intel, or CUDA cores on an Nvidia device. That being said, the actual explicit order that work items and work groups are executed in is entirely implementation defined. I remember we had an intern at one point years ago who came in and wrote a reduction kernel for something else. It was part of a task, and it was working fine. And then he changed hardware. We wanted to like actually start testing it, and we changed hardware. It moved off his PC onto like our CI. Well, let's say CI back in the day that's a bit more of a joke, but it was, you know, we were testing it, and like it just started to fail out of nowhere. Code hadn't changed, and it was because this one implementation that he was starting to run on ran the work groups in reverse. It started at the highest number and kind of ran down from there. And the way that he'd written it would only work if the work groups ran exactly in kind of forward order. So that was very funny, and it was a great lesson in don't rely on the order of work groups. The code was wrong. We did fix it, but yeah, it was sort of very real consideration that we had to care about that. So if you do need to do some synchronization, work items that are within a single work group can be synchronized using a work group barrier. No work item will be able to proceed past the barrier until all have reached it, which functionally means, you know, called that function. And you can imagine, you know, like it's like the equivalent of a wait on the host CPU, you know, waiting for some kind of condition to be true. So, but generally with hardware support. SYCL doesn't let you synchronize across every single work item in a full ND range, and the diagram here shows you that the ones on the left are on work group 0, the ones on the right on work group 1. There's no way to do that synchronization between them. At this point, if you want to do something like that, you have to have two separate functions. You have to split the kernel at that particular point, which again generally comes from like hardware limitations. And not least because workgroup 0 might have entirely finished running before workgroup 1 even starts. So how do you do that synchronization? If you can't even guarantee when they're going to run, and we cannot guarantee when we're going to run, then it's very difficult to try to provide synchronization primitives for people to do that sort of thing. So we talked previously a little bit about sort of memory, and I promised you that we would do more that was hopefully more clear. This is it. So each work item has access to these different kind of parts of memory. So every work item will have a dedicated region of private memory. I think of this as being basically registers. It's extremely small. It's very fast. It's very, very limited. As I say, I think registers of a CPU when I think about this memory. There's a dedicated region of local memory. Local memory is what SYCL calls it, what OpenCL calls it. in CUDA, that would be CUDA shared memory. Every work item can access this memory. You do need to use barriers with some memory fences to be able to observe the stuff that the other threads are doing, but you can communicate through it. Generally, it's going to be quite fast as well. Yes, it's another region, and it's also fairly limited, but less so in registers. And you can query how much local memory a given device has available. And then there's a single there's a single regional global memory. Shared is a bad word to use. It is accessible to every single work item within the ND range. Constant memory is, we won't cover that really today, but it does mention it here, but it's not really, it has been deprecated, I think, from the SYCL specification. But yes, the global memory is very large. Again, that's the kind of sticker, you know, like this GPU has 16 gigabytes of VRAM. It's that number. It's the large region, and whatever you do there is, you know, visible to the host, and with the correct atomic primitives, if you're trying to do some kind of shared memory operations, is visible to other threads in the system. So how do we actually bringing this memory model and execution model together? We change the function that we're going to call. So instead of the single task that we've been looking at so far, we use this parallel for function. It behaves very, very similarly, but there's going to be a couple of like key changes that we will highlight here. So the first is that instead of having no argument describing its shape or the shape of its execution, you have to pass in at least a range, and this would describe the sort of the iteration space. And here we can see that the users requested a 64 by 64 range. So that's, well, how many threads is that? A lot. Is that four? It's like 4,000 threads or something, right? I can't remember.
96.
Yeah. I imagined it would be that, but this is why you should always have the answers written down before. So yeah, this is 4,096 threads in a two-dimensional grid, and we can see if we go to the next one that we now need to know inside the kernel which element out of that entire ND range that we are executing. We need to know. We need to be able to identify ourselves, and this is done in SYCL by this ID class. The dimensionality of it is a template argument, and that needs to be provided, and it needs to match the dimensionality of the range. And yeah, you get this IDX, which will tell you where you are in the iteration space. This is almost falling off the bottom, but if you look at the code sample at the kind of bottom of the page here, this one, the two previous samples simply say, I want this many threads, and it essentially leaves it up to the runtime to decide what the local size should be, and it will choose something. And again, this feature kind of matches the sort of stuff you can do in OpenCL, which lets you, instead of querying what the optimal size would be, you just let it select it for you. However, you can entirely specify it, and I think most kernels these days I would expect to see using this ND range, where you it has two ranges, and that lets you fully specify what you would like the shape to be. So here, you know, like it might, the runtime might say, this is a very simple kernel, so I'm going to have a local size of 256. But you might say, actually, I want it to be split differently. I want a local size of 32, and out of this 1,000 threads. So, you know, that's going to be 32 groups of 32 would be, you're explicitly requesting that here. The one other change that it requires is that instead of taking an item, you take an ND item, because again, you need to be able to express now where you are both in the local and the global sense.
Yeah, let me just emphasize here that while the runtime is fairly smart about guessing the local workgroup size when you use just the range, it cannot possibly know everything about the code and how it's going to be executed. So usually it's better for performance to use ND item and experiment with profiling and benchmarking on what kind of group problem size works best for your computation to really get the best performance.
That's very true. That's very true. Yeah, definitely. The workgroup size can strongly change performance characteristics. It is difficult to predict exactly how it will, but I would expect the optimal value to be somewhere between 3 and 256. I'd be surprised if it lay outside that range, depending exactly on what the kernel looks like. Probably more like 3 to 128. But yes, benchmark, find out, get data, and then select something that makes sense is my is fantastic advice. So thank you, Rafael. If you need the local work item ID, for example, I would need to, yes, exactly. You cannot access the local work item ID if you only have a range. I think the idea there is that if you don't know what you're even getting, how can you rely on it? Again, I slightly challenge that notion because I think you could program local memory not knowing what size that is, but SYCL just says, if you didn't ask for it, I'm not going to let you shoot yourself in the foot, and that's probably fair enough. Does that make sense? Cool. Oh, what happens when you use the basic version and have a big prime number? Do you want to answer this one, Rafael?
Well,
that's the bit that you're into, yeah.
So generally what happens is what Duncan was saying about the last workgroup having different size. Basically the runtime will round up the range to the next sort of multiple of 32 or next power of 2. And then we'll just submit your kernel wrapped in an if statement, that if the ID is beyond your actual requested prime number, then it will do nothing. But it will still submit sort of a range that is rounded up to the next reasonable number.
Yeah, Raval ran into some real bugs with that behavior for quite a few versions and fixed them. So
yeah, if you want to rely on that behavior, please use a fairly recent release of DP++, as we've had some bugs in that.
I think the behavior of I'm pretty certain that if you did that to compute CVP, it would say, fine, you know what you're doing, and give you like 117 workgroups of size 1. It doesn't do this automatically when the specified ND range is not divisible by the specified workgroup size. No, because then you've kind of asked for a problem, and it doesn't necessarily even know. So you could have asked for those numbers dynamically, but it could also, or sorry, statically, but it could also have been dynamic from like user code. Yes. It's mostly not.
Yeah, well, I've seen people do that, and I do that myself sometimes. Yeah,
I guess the thing that's nice.
It is sort of like CUDA then.
I guess the thing that's nice about CUDA though is that you do just say like, I want this many work groups and they're this size, so you can't code it incorrectly that way around, if that makes sense. But yeah, again, this is another OpenCLism where OpenCL said, well, if you look at in CL and QND range kernel, it's got like workgroup size and and the local size, and those have to match. And then you start asking questions like, but why was it like that in OpenCL? And you got to go ask Apple for that one back in 2007 or whatever. Yeah, okay. I guess we will continue. Sorry, I forgot that was it. We've actually kind of covered it. Yeah. Well, that worked out then. Got a lot of questions. If there are any other questions, happily take them now. Otherwise, I will look up and show the next code exercise. That's not the one. It's data parallelism. So this is a sort of other similar task where we can see that on host we have three initialized arrays of size data size. Two of them have some float data, the last one's all zeros, and we want the assert to pass, which is going to check that every result is equal to twice its index. And we want to do this calculation on the device instead of here in this loop. So we're going to have to make the buffers, make the accessors, do the calculation, or you can use USM if you want as well. Either will work, so long as that by the end of it, this assertion loop passes here. If there are any questions about the task itself, let us know. I'll be more than happy to help. Otherwise, I'll check in a few minutes and we can see how everyone's getting on. Is there a way to trigger the compiler or runtime to emit information about the automatically chosen workgroup sizes? So the workgroup size is chosen by the runtime, not the compiler, because it is. Again, this is something of an OpenCLism. So I was talking about the CL and QND range, and I'm just gonna. It's easier if I can kind of show it because it explains where a lot of these design choices come from. So like here's the OpenCL version, and like the queue you want to execute it on, the kernel you want to run, how many work dimensions there should be, and then these. Well, we can ignore the offset because no one uses that, but the global work size and the local work size. If you pass a null pointer for this parameter here, the local work size, then OpenCL will choose it for you. And so like even the SYCL runtime doesn't necessarily know what was chosen if you let it pass it off to that. Yeah, so potentially. The alternative is that if you turn on the SYCL UR logging, you can actually see what commands the SYCL runtime is sending to the unified runtime. And that will, if a work size has been chosen there, then you'll see it. I imagine because of unified runtime, probably the SYCL runtime never sets this to null pointer, it probably always chooses something, and you could see what that was there in sort of a locking fashion. I don't think we define what the metrics are though. Like they've definitely changed what numbers it would choose to calculate before. Well, yeah, and Rafal has patched it when it's been buggy, so it's not like a. I don't think they count it as an observable. I'll paste it in the chat. So if it's, I've said -1 there. If you set it to just 1, it's not like the fully verbose version. If you set it to -1, you get everything, and it's a lot. You can, of course, also the Compute CPP used to try to use Nvidia devices through their OpenCL implementation, and like they broke a bunch of their tooling on that, and that was kind of really sad. Like you used to be able to run like the Insight stuff on OpenCL programs on Nvidia. They broke it, and that's kind of sad. But because DPC++ uses the CUDA backend, to that runtime, it looks just like a normal CUDA program. It is just a normal CUDA program, really. So you can use those to find out what's going on. If you want to know how many threads are actually running, you can just use all those tools. Intel provides vTune, and vTune will tell you what's going on with the CPU and GPU. In the Intel case, AMD have their own profiling tools that I have messed around with a bit from time to time, but I'm less familiar with those. But they all work. There are also, outside of Intel's vTune, there are a whole bunch of OpenCL tracing tools that will intercept the OpenCL calls you're making, tell you about them. Some of those are developed by Intel engineers, actually. Like Ben Ashbaz, I'm going to call it his name, is someone who I think has done some incredible work in terms of being able to show you what your application is really up to under the hood, and to get that information out of it. I suppose the relevant one for today is maybe James would know the answer to this about how available the Insight tracing tools are on Cirrus. I know that it can be difficult because they frequently like to have effectively root access to get at some of the information that's on them. They're available. Okay, cool. So potentially that works, and maybe that would be a good way of getting some reports out. You use them to teach CUDA. Fantastic. Okay, cool. It's the same with Intel. Anytime that I run the vTune and it's like, you've not given me root permissions, and I kind of don't want to, but there's obviously a tension there. I mean, that's a fairly pathological size, though, isn't it? I'm sure we can always improve the algorithm to select these things. Yeah, simple, yes, but pathological.
Yeah, for the implementation, it's easy to find cases where it would go bad, but difficult to find an algorithm that would cover all these cases and perform best. So yeah, as I said, really, if you're looking for performance, the ND range is your solution. And when using SYCL range, it's basically just telling the runtime, here, I don't care how it's executed, just run this in parallel for me somehow.
Certain multi-good versions of the number is pretty standard. Really? Okay. And a simple CUDA grid stride loop will just deal with it. I'm not sure I understand. guess I don't see how you can encode that in CUDA, because you're saying I want this many groups of this size, so it's always going to be evenly divisible, right? Right, I see. I think the Rafael is correct that the way to handle this normally is that you would do the range rounding yourself and leave it in your control. And then you effectively end up with the same, you recover the same as the CUDA behavior. The cost of one if check at the start of the kernel to make sure you're still in the iteration space is effectively meaningless. So, or was in the testing that we did in one of our libraries a few years ago.
Yeah, so again, comparing to CUDA, in CUDA you always specify the grid size and block size explicitly, so you have to program it. So this SYCL range feature, this automatic guessing of the workgroup size, is more of an extra feature that doesn't really exist in other programming models, which is there for convenience, but certainly not for performance.
I can't find the discussions right now, but I'm pretty certain that some of our colleagues have talked about removing the range version and just doing the ND range version to kind of solve this. So. You have made a placeholder accessor. How have you done that?
Yeah, a very good question.
Yeah. Would you mind if I look at your source file in your directory?
Perhaps there's an argument missing in the constructor that
That's
makes it a constructor for placeholder, I think. Is it a command group handler reference that's missing?
Oh, yes, probably. I think that's right. Thank you. Good. Excellent debugging without even seeing the code.
No worries. I've seen that error many times.
I didn't realize that that's... Yeah, okay. That's not great. It used to be harder to do something like that because you had to opt in to placeholder accessors. So if you didn't want one, then you'd actually just get a compilation error. That's kind of annoying. Placeholder accessors are tricky. Realistically, they should be removed. They were helpful when we didn't have USM to do certain kinds of things that you couldn't do. Well, you saw it just yourself there. You didn't have the handler argument, and that still allowed you to construct an accessor. So it let users construct accessors outside of command group scopes, sorry, and then subsequently bind real accessors to those in the at that point. And we used this for interoperability with especially the Eigen library, which Eigen has kind of, because CUDA was there first, it's kind of behaves like CUDA expects to be able to behave. And therefore we had this problem where it was very, very difficult to fit the SYCL memory model inside that. Placeholders were what we came up with. But yeah, I think placeholders should probably be removed. They probably will be. Are you an Eigen fan?
Yeah, I think it's a really nice piece of software. Also, no errors mean no output means victory again.
I believe so. Yeah, I think it just doesn't assert on. Yes, yeah, it just doesn't assert that all of the data is correct. We should. We've
Just have
Not
it
that I'm
print
trying.
victory. Yeah.
I don't. Well, it used to print. That's the thing. It used to print. It used to say success, one test passed, and some people didn't like that. So we went through a whole bunch of heartache removing it all, and now no one knows that it's passed or not. I'm going to pass on that feedback. In fact, I'm going to pass on specifically. You were confused by that several times because it
Well,
helps my argument. No. I almost
I accept
don't.
the Unix philosophy of no, shut up and do your job, and only complain if you need to. But having been in your situation of teaching people, where I have done this, I've hit this like, how do I know it's worked?
Yeah.
And I've switched to any like training code. I have to be very chatty and reassure
Yeah.
people.
Yeah. It used to use Catch2 before, and Catch2, you know, each one was like a test fixture.
Nice.
It is nice. It is really nice. People didn't like it, so it got killed.
I'm sure you can
right.
find more suitable things for some cases, but as a default, it's pretty good.
I would agree. So, yeah. So we've ended up writing our own blooming assert that just checks whatever condition you had, and yeah. Anyway, it's fine.
Yeah, and your assert just it lets you know there's a problem, but it doesn't do it nicely. It doesn't do what catch does and actually show you the fact that you've got doesn't print the expression, right? The way catch does.
Yeah. Oh yeah. Well, we tried to add support for that, and it was just. It turns out
I'll use someone else's code. It's decent. Good enough, surely. Sorry. Shut up.
Yeah, as I say, I'm gonna. We do take this feedback on board, and the fact that this is the first time this has been. Oh, that's not true. They did it as supercomputing, but I don't know how that went. But yeah, I'll let them know that removing it has actually made your experience just a little bit worse and like harder to know, because it suits my arguments to be able to say that. So thank you.
Yeah, good. Happy to help. And what was the incantation to get it to say about its block size and stuff? Or work item size, sorry, work group size.
So is
it the SYCL UR trace thing?
That will, that shows every single kind of. The SYCL runtime makes these calls into unified runtime. Unified runtime is the bit that papers over the difference between all the different backends.
And I do that at runtime or compile time?
Runtime.
Okay.
And that's an implementation detail of oneAPI, so it'll only work for this.
Shouldn't it be oneAPI _ trace then? If it's not a SYCL.
If you would like to start a holy war, you go first.
Yeah, sure. I'll do that. It's fine. Not like I've got a day job.
Yes, that would probably be more correct, but there's a bunch of historical reasons why it's not worked out like that. They've managed to change some of them. You can override the device, for example, now with oneAPI device filtering. That properly says oneAPI, but
oh, I have a lot of messages to decipher now.
Yeah, so that basically tells you about every single call that your thing makes, and it will. One of them will say it'll be UR kernel launch. I think would have the actual data in there about what it was choosing to run. Okay. I don't know if there's an easier way to get it out.
Yeah, I've got all my Insight tools installed, so I could easily pull it back, but.
Mm-hmm.
So I've got a work for my kernel launch. I've got a work dim of 1, a work offset of 0, work size 1024. I can't see anything that looks like a block size or a work group size or.
Oh. If you give me a minute, I will go look up the code and find out what's happening, because that Could be correct, but isn't what I expected.
Okay. Oh, there's something just before about kernel group info. It's not looking great.
And there's not. So there should be P global work size, but there's not a P local work size. I'll try this myself.
Oh yeah, the P local work size is null putter. I just glossed over it.
Interesting. Okay, right.
It was
so in that
just
case,
a null. I just skipped it from my brain without noticing.
interesting. In that case, I can tell you that it asks for CL get kernel workgroup info. Right. So what it tries to do is, if the local workgroup size is 0, it queries to find out if the compiler has inserted a suggested local workgroup size, which is a feature that is available in a bunch of backends. And if there is, then it uses that. And then if not, I guess it will do something else.
I think the guessing of the workgroup size is an implementation detail of each backend, even in this lower layer of unified runtime. So I think indeed you cannot even see it in any of the official API calls in unified runtime. I think it's all happening really just in the implementation.
Locida has to choose something, right? So we could find out what CUDA does.
Yeah, but still you won't see that in the UR trace, because UR trace only prints the UR API functions.
That's true.
And that value is not passed anywhere as argument in this API.
Right. Right, I see what you mean. Yeah, but you would find it in the the Insight tooling.
Yeah, absolutely. So that's probably the easiest way, indeed.
I can tell you that for the CUDA backend, it looks like UR will call, there's a function Q occupancy max potential block size, and then it does some rounding of on that value and chooses that as its local size.
Is that based on a particular kernel, or is that? Because there are all these complicated CUDA runtime functions that I never use.
Yeah.
Yes, it does take the kernel as a parameter because it considers the amount of registers it needs to use. And
Yeah,
stuff like that.
exactly.
Yeah.
Yeah.
And the shared memory usage.
Yes, I can tell you that it takes into account the kernel as well as the kernel's local memory usage,
Yeah.
as well as some notion of what the minimum grid size should be, but I don't know what that is in this case. Yeah, and then it does this 3D rounding to get that. So yeah, there are bits that we'll try to deal with this. Sorry, so it sounds like people have at least something running or have several things running, and it's being very, very quiet. I will definitely be bringing some to my colleagues because it's not good if people are like, well, did it work? I don't know. Has anyone not been able to get it to work, or is anyone still seeing like exceptions or problems that we can help with? I'm hearing no complaints, which makes me hopeful that everyone's got something running. Because this is our first sort of proper look at what I would call real code, even if it is sort of very simple. We can have a glance at the solution here. This one using buffers, and you know, it all makes a lot of sense. We have this the buffer, the range. We submit a kernel which is doing more or less the same addition, but instead of just looking at the first element, it looks at the element corresponding to where you are in the iteration space. I would love to know what's gone wrong with this formatting. This is horrendous. You know, it was Hugh that removed. It was Hugh that did the formatting as well as removed catch 2. So he and I are going to have words. I love Hugh, but something's gone wrong. Yeah, so instead of just looking at the zeroth as in the previous one, it looks at the IDX element. This weight is still not necessary. At the very least, this could be a Q wait and throw, and then it does insert, and so we get the correct answer. So hopefully everyone was able to get something similar to that running. If not, let us know, send a message, whatever. But I guess for now, we will move on to the next portion of the training. In terms of where we are in the day, we could have a small break here, but it might just be best to keep going for now so that we're kind of still on track because we're here at the moment in terms of the plan for the day. So if you'd also like a break, do let me know, but I figure to keep with the schedule as is, we can keep going. Okay, cool. So here's our next set of slides on asynchronous execution. So in these slides, again, not too long, we'll learn about encoding commands asynchronously. We will learn about the different reasons and ways of doing synchronization. As we've already this might be quite quick because we have already looked at it a little bit. We've seen the dot wait and so on. And we have mentioned before that all the commands that are submitted to the queue are done asynchronously. The submit function returns immediately, and the actual command is then executed in the background thread. And this would include individual commands like memcopy, as well as collections of commands derived from a command group. And this would be the implicit memory movement that arises from using buffers is occasionally going to cause stuff like a memcopy to be issued because you're using data for the first time on a device or whatever other thing. You know, there's going to be potentially a bunch of implicit commands on top of that as well. Oh, thank you, Rafael. So the reasons why you might want to is potentially to just await for the kernel function to complete. This is useful when benchmarking because you want to know how long your kernel took to execute. In my own time at CodePlay, I've kind of done things both ways. There was one project where our benchmarking did await on the host side, and I think we settled on that because it was kind of the most sort of real world, like you could query. So you can query, you can actually ask the device, hey, when you ran that kernel, how long did it take? You guys are familiar with NCU, it can give you the same information. And that will give you a number, but it's not necessarily the whole story in the sense that the user still doesn't have the results, right? Like there's always going to be, a delay before the kernel starts, and there's going to be a delay after the kernel is done. It might be very, very small, and we want to try and pack as many commands in there as possible to make sure it's always doing something, but it's not the whole story. So when we did our benchmarking, we would like run one command, wait, and record the wall time either side of that. And that gives you a sort of like, definitely things are done by now kind of number for that. It might be to await results of some other asynchronous computation here, or you might be looking to check to see if there were any errors associated with the kernel at all. So this might be when you're in a debugging kind of mode, you might edit your code, say, I'm gonna make it synchronous. I'm gonna wait for everything to happen so that I can find out about errors as soon as they occur. And so there are two main ways to synchronize the kernel functions. That are explicit at least. So you can call wait on any event that you get from including a kernel command. And so this would be like going back to data parallelism here and looking at the solution. Here we call .wait in the event, but you can actually, you can capture it and just say auto event equals default queue.submit, and that will be the event, and you can call wait on that later. But you can also just do it like this. Oops, sorry. One block of 1024 threads. That makes perfect sense. It's a very simple kernel, very low resource usage. Yeah, for sure. That all makes sense. And I'm glad that it's simpler than reading the bones of trying to get unified runtime to tell you. So you can do that via the event. But you can also call wait or wait and throw on the queue itself, which issues kind of like a global stop. Again, this function is thread safe, but if you don't synchronize, again, you don't necessarily know where you're waiting. You've got multiple threads submitting to a queue, it is safe, but when someone waits, you don't necessarily know what has been submitted if you haven't synchronized around that yourself. So yeah, you can see here that in the sample code here that you can explicitly call wait at the end of each of these command groups, and that turns it into a sort of fully synchronous lump of operations. And that's what we've been doing so far this afternoon. This is the example of using the kind of global stop on the queue by saying just wait after that. Functionally here, it is the same. But it will wait for everything on the queue rather than just that one case. This is a good bullet point, which was talking about copying back. Again, the runtime is lazy and it won't do stuff it doesn't think it needs to. So a command group might include an implicit copy here. highlighting is useless. It might include an implicit copy here, or I would expect it to, because we've never used this buffer before. So I would expect it to have an implicit copy at this point, but it won't have one. It won't issue one afterwards. It won't issue one back because you might not need to. You might be about to do another kernel on the same device, therefore you might not need to move anything at all. So it won't do it unless it thinks it's necessary. We can see here these kind of shortcut functions used with USM. So here you don't need the full command group handler dance. You can just call the parallel for through these shortcut functions, and so you can just call wait on those, and that works too with the queue as well. And you can see here actually that one of the things you do need to do at the very least is this is where it's quite heavy-handed, but you need to put a wait in here, otherwise this kernel potentially can just go off and run, and you won't have the data there, so that would produce incorrect results. So you can also synchronize with data, and this is probably a sort of generally better way of doing it. And so when using USM, you can synchronize the same way by calling waits. When using the buffer model, they don't automatically copy back, as we just noted. Sorry. So you can instead create a host accessor or destroy the buffer. And I believe we have some samples here. So again, USM, you're copying from the device to the host data member, and you've got your size. You can just call wait, or you can do a queue wait after you do the thing. Either is absolutely fine. In the buffer model, here you can see that a host accessor will give immediate access to the data that's been managed by the buffer in that host application. And so here we create a new scope, another new scope, and we say that we want host access to this buffer. And then you just get another accessor, which you can access in exactly the same way. This says IDX, but you need to name, you might loop over it or something, you know, or you need to, it behaves very much like an STD vector at that point. This is kind of like implicitly aware of what's going on, so it will wait for any kernel functions that are currently accessing the buffer buff to finish, and then we'll have already enqueued a copy back to the host if you did this while there's some device computation going on, and it will wait for both of those. So by the time that your code reaches this line, the data is all there and ready to use. This is fallen off the bottom because apparently our formatting is broken at some point, but it will block other accessors using the buffer data until the accessor is destroyed. And this is like a little bit different to the device side thing, which is nice and asynchronous. Obviously, this is not asynchronous. This is exactly there on your host thread. So that's why here we actually have this new scope. If you didn't put the scope, then the accessor wouldn't be destroyed until the buffer was also being destroyed, which means no one else would ever be able to access it. And you can deadlock your application if you do something like this. So you've got to be slightly careful to make sure that you don't leave host accessors alive longer than you need to. Otherwise, potentially you can cause problems. It's also sort of fairly smart in that I believe, actually, I need to check this. I think you can set some other arguments on the buffer so that it will use the data pointer like as its own storage, so that when you copy this, it then wouldn't do another copy back. But you might, yeah, I'd need to check exactly what the behavior is for that. There are ways to get, you know, essentially as minimal copies as possible. So. And here we can see another sort of similar example where, again, we have this explicit scope around the buffer here. When we reach this point, the buffer will be, well, I think someone's edited that. That should say auto, because we need it to be destroyed at this point. So I'm going to make a note to edit that as well. But you know, if this were an automatic duration variable here, then by the time it reaches this closing curly brace here at the bottom, it will be destroyed, and that will cause the another wait for everything to be synchronized around that there as well. We've already looked at asynchronous errors, and any asynchronous errors can be produced during any of the synchronization methods with that. So anytime that you call wait, potentially that could be notifying the system about something that has gone wrong asynchronously. So the best way to ensure that all errors that have been caught is by to call wait on the queue, or indeed wait and throw on the queue, and that will give you every error back that could have happened in the meantime. This is especially true with CUDA, which has that rather nasty habit of returning error codes from functions that you had called previously, and I really hate that. So at least doing like a kind of global queue wait is a good way of getting that information back as soon as possible, but you generally in real production code, I guess, don't want to do a queue wait all the time because it's gonna really slow your application down. Errors are pretty rare, so it's normally not a problem, but it can trip you up if you're not expecting to get an error from one function because that would just happen to be the one that the runtime called. So yeah, yeah. The next slide is on questions. So again, please, if you have any, then ask away. Otherwise, we'll start looking at the next example.
Actually, I didn't realize we don't talk about it in these slides, but there's another way of synchronization when especially useful with the USM, where you have the events instead of calling wait explicitly on the event, which makes your host application just stop there and wait. As instructed, you can pass the event into the command group that you submit as a dependency. You can call handler depends on, that's the member function of the handler, and then the kernel that you submit will wait on that event to happen before it executes. Meanwhile, your host application can continue doing other stuff.
So yes, that's a very good point. It doesn't come under this because it's not really synchronization, but yes, that is a very, very good point. If you're using USM, you can use events. You essentially, and there are a bunch of functions that would take, most functions will take a vector of events, which are the events that it should depend on before executing. And it uses that to essentially, once again, form that graph, as we were talking about earlier, that graph of dependencies in the same way that buffers do. Again, I'm a very lazy programmer. I like that buffers do it for me. But you can recreate that behavior manually when using USM, which doesn't have the kind of buffer model semantics. So yeah, but that is a good point. We can look it up and talk about it today if folk are interested in seeing that. It's not part of what we have at the moment, so, but it's easy enough to look up. Yeah, so so the next one is synchronization. So let's have a look up the, sorry, asynchronous execution, same name as the lesson. So in this one, I believe the intent is to synchronize on the different operations that you're doing. It's recommending you start with your code from the previous exercise, or at least from exercise 3. Right, yeah, from exercise 3, which was the, yeah. And then, you know, use that code to force the correct synchronization across a bunch of different operations that you're doing. And the README, I think, has some more details as well. You might, for example, using the buffer version, want to call a host accessor and then see how that, changes the way that the program executes and so on. Yeah. And again, if you have any questions or need any help, please just yell out and we'll give you a hand.
Sorry, what are exercises 6 and 8? I'm a bit confused because we've not been using numbers, and I don't think I've done 8 exercises.
Completely fair. The exercise that we just did there on data parallelism was the 6th one, so it'll be data parallelism there. Okay, I'm going to make another note to take a pass over these exercise numbers because I thought they'd all been removed.
And to add to your woes, inside the source, it's saying use your code from exercise 3 to start with.
Yes, so exercise 3 again is I think it was like the 2nd lecture that we did. 3rd, okay, managing data.
Yeah, so your README says use 6 and 8, and your source says use 3.
We changed a bunch of the names. I thought
yeah,
they caught
it's
all of them.
easily done. It's
it is this pull request.
You know who to blame. Git blame.
Well, we can find out, but it's fine. Happens. So yeah. Oh, you've asked it. Oh, right. You used host accessor to initially. Yeah, for sure. I mean, that's. I guess that's kind of half the point. Is that like these functions are designed to be fairly applicable and useful. So if that worked for you, then great, you done it. I guess it's partly about being able to suit the needs of the application or the library. Yeah. Have people managed to interact with the synchronization stuff? Tried some things. Hopefully not caused any deadlocks. I guess checking briefly in with the solution. I mean, it all makes a lot of sense, but you can see, waiting, throw asynchronous, caching exceptions, and wait, hold on. Oh, that's data parallelism. I'm looking at the wrong thing. Thought that was confusing. I guess this one has a lot of different implementations, but you can just see all the different sort of ways of forcing some kind of synchronization on the computation that you're doing. It may be worth looking at this if this is unreadable. I think the worst part is that I accepted this merge request. I think it's my fault. I will fix this. But yeah, you can see how there's the different ways of synchronizing and stuff there, and that, you know, generally the different ways of waiting or synchronizing. And of course, you know, the sort of, as Rafał alluded to earlier as well, the best way of doing all this is to use events so that your host code never waits until I suppose the final point where you check the answer, or until as late as possible. So yeah. Are there any further questions about that? Anyone stuck? Or even if you need more time, but doesn't, whatever most makes sense for you guys. Still working on it? Okay, well, let's give it a couple more minutes then. We can see where we get to. Maybe start again at about 22. I think. Let me just check the. Yes. Yeah, that'll be fine. Yeah, we're fine. Hello again, everyone. I guess we might move on now to the next lesson. If you'd like to talk about it some more later, Demir, do let us know. But I guess you know, synchronization is important, but you know, there are plenty of ways to tackle it. I guess so. That can be explored maybe later a bit more fully. So I'll open up the next lesson. And so this one's going to be ND range kernels. And this one, we're going to look at a particular ND range kernel. I do need to just note something down quickly. Sorry, just a second. Thank you for bearing with me there. I was making a note for something to do later. Right, so let's get on to it. So some of this content is similar, we've seen before with the execution model. There are parts of this that are newer, or rather that cover some different content. So we mentioned previously before accessing the data with accessors, and we saw before that you can just pass in that ID from that indicates which part of the iteration space that you're in to get the data at that point. And that is helpful, especially if you're doing ND range. If you're doing an ND range which has actually multiple dimensions, like a 2 or 3 dimensional iteration space, it kind of handles that for you, and that will do a row major calculation to get the final address. However, you can sort of do that manually by using a 3D accessor where you do multiple subscript operators to get to the correct part of the accessor as well. You can also call this get pointer function, which will return a device pointer. You can only call this function inside the kernel, and that will give you a simple pointer, which again you can dereference to whichever part that you need. And I think we have, so we have some examples here of simply using the ID directly to get the index. But here you can see some other ways of doing it where we we grab the pointer from each of the accessors that we have, and then use a linear ID calculation, which essentially just entirely linearizes in a row major order your space within the iteration space, and then use that as a simple pointer and offset address calculation inside the kernel. And these are all like equivalent ways of doing the same thing. But perhaps you're working with a library that only does pointers or something, or there's maybe there could be reasons why you might need this or a different interface, or maybe you want to unify some parts of the USM and accessor using code. There's different reasons why you might want it, and you can do it using these. This is the kind of sorry, just once. Just very quickly need to check that I've not opened the wrong file here, which I think I might have done. Yes, sorry, I've embarrassingly opened the wrong file. So taking some of the things that we've learned here, one of the tasks that we now have is for an image convolution, which is a kind of more interesting sort of computation to attempt than vector adds and so on. So we'll cover that now. I imagine you guys probably all very well know about image convolutions. but we can briefly cover this and what it would look like, at least in kind of a SYCL sort of case. And here we can talk about, I guess a lot of this content is for, I guess, originally aimed at people who are less likely to know about essentially stencil models. So you guys are probably far ahead on that one. The algorithm is, of course, embarrassingly parallel in that each output pixel can be calculated independently of any others. And it is very computation heavy, especially if you have like a very large filter or whatever. There are lots of operations done each time. And it also requires a lot of bandwidth. So there are a lot of like really key aspects for the that make this a good computation for GPUs. The standard applies, which is that we will be doing some sort of stencil operation, looking at the surrounding pixels, multiplying them out, summing them, and then using that to modify the image data at that point. Yeah, and this is like the numbers for an approximate 3x3 blur. And if you do that, you get your previously sharp picture, and it becomes quite blurry. These are some of my now sadly gone from this world colleagues. Sorry, the dogs of my colleagues are sadly moved on, but it is a nice picture of them out in one of their parks nearby. So yeah, and so you get this kind of blurrier image of that. So the code in question looks somewhat like this, in that we have both the input image data, which we've left one in the repository for you to use. I think that same picture is available. The filter data, which is going to control what how the blur should look. We copy both of those to the GPU, and then we operate on each of the kernel takes the image in the filter and uses that to produce the output, copies that back to the host, and then we write it out to the disk. From this, we can see, like using this diagram, we can see that we don't need to copy the image input and the filter back because we're not modifying them. And similarly, the output data doesn't actually need to be initialized at all, because for every pixel in that, we're going to be writing something new into it. So we have provided a sort of very naive implementation. We're not saying this is like the best code in the world. It's definitely not, but it will be kind of the basis for like some of the later stuff. And we can see exactly where we get to in terms of the later lectures, but this is like the kind of starting point for a few of the later slide decks. It does come along with this so-called STB image library. It's just a very simple like thing that reads and writes the image. And yeah, there's this reference image, which should still be in the repository. You can use whatever image you want, but this one's available and is the right size. And then I believe it has some hard-coded paths that it tries to write stuff out to. There is like a utility function that was again written by my colleague, which does it will generate the filter data for you depending on what kind of filter you want to use. So identity is just it will return the same as you put into it, or you can blur it and you can have what kind of width of blur you would want. So yeah. It does benchmark it, so we can see that as we increase the filter size, the amount of time taken by the kernel is going to go up. This is on quite an old Intel GPU, but it's less about the actual raw numbers and more about the shape. That as the convolution complexity goes up, the time goes up quite alarmingly. Yeah, we can think about ways of improving that as well. The thing to look at now is image convolution, the image convolution sample, and there's this reference code in it. I'd say we can spend 5 minutes, maybe a little bit longer, opening that and having a quick look. familiarize yourself with the code, and we'll see about getting on to the next stuff after then. Are there any questions in the meantime? Okay, great. Well, I'll check in again in 5 minutes when we've had a chance to look at the reference code from here. Fatal error stb image.h2. No, it should be. Let me just check. It should be there. It might not be there. Oh, that's my fault. Because I provided a tarball, it's missing one of the files. I hadn't thought of that. Yeah, it's not in the tarball. It's because it's a submodule in the SYCL Academy repository, but I made like this is just a normal GitHub release, which means it won't have that file. So if you do a git clone, you'll need to do a submodule init, and then, or you can do a git clone recursive to get all the stuff. Oh, with recursive, really? I mean, I don't know why I said that, like I didn't believe you. I fully believe you.
I think the benchmark.h is in the utility directory in the repo. It's just maybe that you need to add the include search path in the compiler invocation. Minus
if you're using
capital E.
Yeah, if you're using CMake, that should work. But if you're using the ICPX command, you'll need to pass an include path to the utilities /include. Okay, right. That doesn't fix the STB image problem, and I think the best way to do that that'll get the files. It's quite an old version that we use. There is a potential that the API has changed, though you never know, maybe we're lucky. If it has, I'll copy the right version. Onto service. Yeah. Actually, I suppose if you do that, you could actually check out. Hold on, I'll paste the short thing. So the commit to checkout is this, and that should be the exact correct commit that we use. Again, I didn't even think that using the tarball instead would mean that you'd miss out in this file, so that's my fault. I'm sorry about that. Okay, right, cool. Yeah, that should be the correct reference. Yeah. Right. I think your second question, that doesn't make a range from 1 to channels. It makes a two-dimensional range, the first dimension of which goes from 0 to 1, and the second goes from 0 to channels. I think that's what you're asking. The first question, I'm going to need to go and look at the code because I do not remember it. Do you have a line number that I could quickly look at? Yeah, it does. It does. It's more pragmatic than mathematical. I think is what I would say. Very in buff range. Yeah, it'll just do a pairwise multiplication for sure. Yeah. I think that expectation is sort of reasonable from a mathsy point of view. I think from a I want to the problem is that there's no like 5D ranges or 6D ranges. So if you multiply two 3D ranges, what's going to happen, right? So like it kind of has to be pairwise to make sense, I would say. Though again, there's this talk of you would have implemented it with a 3D range. Right. Oh, you mean like width, height, channels kind of thing? That's probably fair. That's probably fair. I didn't write this. What does range multiplication mean? It simply does pairwise multiplication of the elements. Yeah. Why? As I say, pragmatism over any kind of mathematical niceness, but it allows you to manipulate them, right? Like if you want to do a very simple kind of like scaling or something in a particular dimension, you can do something like that. For example, say you wanted to like multiply the middle range, the middle element of the range by 10 or something. You could create a range which was 1, 10, 1, and then do your multiplication, and that will scale it up. Because it also supports things like multiply equals. So.
But what does a range represent?
So the range.
What does it mean? what does a range mean to SYCL? I'm struggling to understand why multiplication is even defined.
Well, so I mean,
think of it as just a vector of 3 numbers.
Then I object to the concept of multiplication for vectors deeply.
Okay, not a mathematical vector, an array, as in the programming array.
Well, then don't. But why is this defined for a range? What does it mean? I know I'm being pedantic, but I like to know what things mean in a programming language and a library like this. And I've come to accept the standard library's use of vector, and it deeply upsets me every time I use it. But, you know, I need to go through this coping process for SYCL now.
I mean, I think that's definitely fair about the STD vector as well, for sure. In this case, for example, you can see here that it uses the input image dimensions. Basically, I think Sebastian is correct. You could absolutely do this with a 3D range, and I will find my colleague online tonight, and I will quiz him deeply while pouring a drink to find out why he's done it exactly that way.
You'll deserve it, yes.
Indeed. You can see here. So basically, what it's doing is it's doing like a manual striding of the channel data into the image data, essentially. So and that's why it's like the image width dimension is becoming channels times longer to represent the fact that for each part of the width dimension, there's actually going to be, well, it'll be 3 because there's 3 channels. That is absolutely a fair enough question. Perhaps he wanted to maintain the sort of 2-dimensional nature of the image and like kind of show that. It might have been adapted from some code that was doing like a grayscale blur. I'm really not sure. Sorry.
Yeah.
In terms of like what's the meaning of multiplying a range, it's just that it lets you manipulate them against each other so that you can do stuff with them, which might be, you know, like staggering it or what's the word I'm looking for? I'm feeling
the ranges always start from 0 as well.
Yes.
Okay.
I guess, I mean, range in terms of storage is, yeah, it's just simply 3 int values. Sorry, 3 size t values, strictly speaking. Which
basically it's
so this is a size tuple. It's not a range.
Yes. That's a sort of unfortunate naming in the SYCL standard.
Yes, and I know once it's standardized, you're kind of stuck. But
exactly. Not a big fan of the name either, but yeah, basically it represents size. It's like n-dimensional size t type.
Yeah, that's
well, yeah. So an ND size sounds like a good name for it. Just for me to do a quick search and replace before I have to go any further.
The committee is looking at renaming some things in some quite wild and
yeah, because this is fundamentally, it's not a range, right? This isn't a start to an end. This is just the end only. That's the only thing you can control.
Yes, but it's yeah, ND size t is probably a better name, sure.
I'd accept dropping the t suffix as well, but yeah.
So just a ND size, sure.
Sorry, we're bike shedding this.
No, I do appreciate that. Looking at SYCL range now, I tell you, right, see, 10 years ago, this made perfect sense to me. But I appreciate now that looking at SYCL range 1,32 does look like different things to my eyes now. Not that I was that heavily involved in codifying SYCL, but I was there in the room. That does look very different now in the post ranges world of C++. So I appreciate that things are a bit potentially, if you're coming from other disciplines as well. Maybe we should suggest that. Okay, I'm going to make a quick note of that one.
Yeah, sorry, I've done a lot of C++ and a fair whack of CUDA, but I've never done SYCL, hence my presence here.
Sebastian, you're asking, the global range is width height, but the buffer range is height width. You may have discovered a bug. I cannot promise that you haven't. There was a whole, it's not worth going into right now, but there was a whole thing where some of the indices get flipped. I don't think that's useful to dive into right now. So it's possible that one of them was flipped and one of them wasn't. You may have discovered a bug. The input image is square, so we wouldn't know. So it's the outermost dimension is the fastest changing. And that's why actually there's this index flipping thing, because if you have a one-dimensional thing, it really is a three-dimensional thing, just like the other dimensions are both one. So it does some bookkeeping under the hood to make sure that the fastest moving dimension is always the outermost dimension, as when you look at it in SYCL.
So for the memory coalescing?
Yes.
Sorry?
Items which are different in the outermost dimension will be next to each other in memory.
So it's layout right, to use Khronos style terminology. As in the rightmost index varies the fastest as you step through the linearized memory.
Yes. I've never used Khronos, but by your description, yes.
I'm never a fan of row major and column major, because when you're drawing a matrix, you normally have your indices transpose. You do row column rather than X, Y. That always confuses me.
We
like
filled whiteboards.
Khronos language of layout left and right because it's unambiguous and doesn't depend on any other convention.
Oh, that's a fantastic link. Thank you, Rafal. Yeah.
Oh yes, exactly the sort of thing I care about. Lovely. Oh come on! If there's no point doing this if you're not trying for good performance.
Oh no, yeah, 100%, and that's why there was such a big argument originally about working out that we were accidentally sending like the slowest possible thread size to the various GPUs. So yeah. I'll be honest, for the most part myself, when I'm doing stuff like this, I think in 1D, I do everything in one dimension, and if I need to do any kind of indexing, I just do it by hand because it's just how my brain works. I don't. It can be useful to do the ND stuff. You can certainly use it as a shortcut, but again, I think it's really just one of these hangovers from the original graphics APIs that we talk about it in this way. So I think the
so the indexing here is the opposite of CUDA's, right?
Yes,
because CUDA goes X is fastest.
That's right.
And then Y, then Z when you're doing your CUDA, which is okay.
904.
Okay.
Interesting.
That's coalesce, isn't it? Because you're using the rightmost index is the one varying. Oh, it's not varying per thread per work item though, is it? Yes, because we've got array of structs, not struct of arrays here, right?
Yeah.
Yeah, exactly.
This code has
Sebastian.
gone very strange.
Are we filtering each RGB components independently? Is it RGB or is it RGBA? I can't.
Looks like
there
it's
was
RGBA.
a 4 going on there, wasn't there?
Yeah. Yeah. It looks like all of this code has been touched at some point a few years ago. So I'd need to go back and like normally folk just run it.
Well,
I will investigate this and figure out what's
does
kind of
this
going
code
on.
only work if you have 4-channel input as well?
Yeah, it
We're
assumes
accumulating a float sum, which is a 4 vector, and we're doing stuff element wise on that, and then so if I put an RGB only in PNG in, this goes horribly wrong. Let's find one.
Yeah, certainly, yeah.
Yeah, so that
it does.
Your dog picture does have an alpha channel, so that's RGBA.
Yeah.
Let me find a PNG from somewhere.
Yeah, this code is definitely hard coded to the format of this particular image, just to remove.
Just inconsistently. Sometimes it uses channel and sometimes it fixes it 4.
Well, has anyone managed to get it running like properly? Does it? Hopefully it's.
Oh yeah, I've got blurry dogs already. Yeah.
Oh, that's good. Good. If the code had bit rot sufficiently that it doesn't even run anymore, I was going to be really upset. So.
No. I'd have been complaining already about that. Don't worry. Sorry.
No, that's fine. Okay, sorry, so is there anyone who has not been able to get this running or it isn't working for or anything that's going wrong still? Okay, so it's working. Great stuff. So the where have I left? I've got too many Firefox windows open. I keep on looking at the wrong one. Losing my place. So we have about half an hour left or so, I suppose, before the end of this session. So I guess what I would say is we can look at the next step of the image convolution bit if you guys would like, or we could talk a little bit about USM if you wanted to look a little bit more at that and how that compares to the CUDA version. Though I think you've seen a lot of it just in the code that we've had today, and I figured I'd leave that one up to you. Okay, so yeah, the last slide deck I promise that I'll put you through is the local memory, also known as shared memory in CUDA. That's what the hardware maps to. I don't remember what AMD referred to it as. Yeah, this can be very important for obtaining peak performance for certain classes of problem on certain bits of hardware. So we'll cover it in these slides here. So we'll learn about tiling into local memory, and we'll also learn about how to synchronize within work groups, which is important when you're using local memory, because again, you can end up in a situation where you read stale data, for example, if you're not careful. So as we were looking at earlier, we have global memory. It is very expensive to access. It is going to take a long time. GPUs have very incredible bandwidth, but the latency is horrible. Even when you coalesce global memory accesses, if you are accessing the same elements multiple times, it can be expensive. So ideally, we would want to try to cache those values in some lower latency, perhaps closer memory. And so briefly recapping, we can see that when we're loading the image data from kind of nearby threads, clearly we are accessing the same data over and over, and we would expect it to be a coalesced load because nearby threads are loading nearby elements. Nevertheless, there's probably still something we can do better here. And so here we've highlighted with the handy dandy red oval. The solution is the local memory, which we talked about before. It is going to be generally on the chip. It doesn't have a cache. Actually, in some hardware, I think it functionally is a cache, and is much lower latency, but it is much smaller, though there is more of it than private. I suppose it is worth noting that some bits of hardware don't even have local. I think there's like a query you can ask for, which is like, you basically say like, is local memory just more global memory? And that's going to be true on like CPUs, if depending on the implementation. There was an ARM chip from years ago where that was also true, so that instead of using local memory, they just had an incredible caching system that did a pretty good job. So in those ones also, you don't want to use local memory, but for dedicated GPU hardware, like Intel's, like Nvidia's, like AMD's, local memory is a great solution to getting peak performance out of the hardware. So the kernel is mapped to many work groups, as we saw before, and each work group has its own amount of local memory. So what we want to do ideally is to split our input data into tiles, and a tile per work group, and then use that local memory for that portion of the image. So I believe this still works, but if you look at SYCL 2020, this has now been aliased to SYCL local underscore accessor as well, and that just takes a range to define what size it should be. So yes, unlike regular accessors, it says they're not created with a buffer, there's no associated host memory, they're not accessible from the host. They simply allocate memory per work group for the duration of the entire kernel. And the range that you provide it is the number of elements of the specified type to allocate per work group. So local memory can be used to share partial results as well between work items. But when you do so, you do need to make sure that you synchronize between your writes and then reading of memory to make sure that all the work items have actually reached the same point in the program. That was someone raised their hand, or is that?
Yeah, that was me. Sorry, I was just going to ask you. So we have to allocate our shared memory before we do our task or parallel for.
As an accessor, yeah. Okay,
or is it inside the kernel?
The complicated answer is it's both, because there's now an extension that lets you do it inside the kernel, but it is before and with the, when you use the accessor way of doing it, yeah, it's an accessor with all the other accessors. It has it uses the
inside the work group. No, sorry, the command
inside
group.
The command group scope. Yeah.
But before you have your kernel. Okay, thank you.
Exactly. yeah, it uses if you see here falling off the edge of the formatting again, the
I've missed
handler
that before. Yeah.
is,
Okay. Yeah.
yeah, one of my colleagues made some improvements and then hasn't merged some of these that would fix a bunch of these bugs, but I'll tackle them before Christmas again, because he's been sitting on the patch for a year. Yeah, so yeah, I think this will have some samples to show you exactly what it might look like. At the very least, there's code samples that show the same. So yes, we have no guarantees about what work items will execute when, and particularly they won't necessarily all execute at the same time. But we do want to be able to share results with our work items in local memory. And you might want to do this for like voting algorithms, or for implementing like like any or all, or these kind of predicates. These workgroup level functions have been added into SYCL 2020, but there might be some custom thing that you want to do that requires communication, and that's absolutely fine. You can do these, and you would need memory that is shared to be able to communicate these results. So the problem is that you might run into a situation where a work item would try to read a result that has not actually yet been written, and that will be a data race, as somewhat indicated by this diagram. If the blue thread here is trying to read that block indicated in red, it hasn't been written to yet. So the way that this is solved in SYCL is with a workgroup barrier. This looks a lot like OpenCL. I think, again, those of you that have done CUDA will be familiar with sync threads, I think is the primitive. Whenever there's a barrier, the work items will wait at the barrier until every single work item inside that same workgroup have reached that point. So here in the diagram, you can see that the execution of these four on the right-hand side, stops. Then the next four are slotted in, hit the barrier as well, at which point they can all continue executing after that. And yeah, when they've reached that barrier, by that point, they have all made the write of their data to the local memory. And then when we get to try to read, it's all fine. We've managed to get a safe read off after that. As we alluded to before, there's no global communication for this, and it does not apply across workgroup boundaries. If you have one workgroup doing some writing to, like, say, global memory, and you try to read it in a different workgroup from another work item, that is a data race, and you can't really guarantee that that's going to work if you're relying on specifically that bit of information. You can do, now I don't think that we cover it in the, well, I was about to say about atomics. Now that's slightly different in the sense that you could have one defined memory. So again, if you were doing, you can do a reduction, where you have like one memory location that you reduce to. But that guarantees that the answer is right. It doesn't tell you about who or who hasn't, like who has or hasn't executed yet, right? Like it doesn't, if I'm doing like a reduce over add, and I just add my result, and I don't know who else has previously added before or who's yet to do their sums, right? So it's less about, that still doesn't count for certain kinds of global communication where you need to know that, for example, an entire workgroup has written an entire section of memory that is their own memory, if that makes sense. I'm maybe not explaining it very well. Does that? Am I making enough sense for you?
Yes.
Okay, cool. Yeah, and so the local memory is local to that workgroup, to no other workgroup. You can't access any other one. You can't access it from the host. It's just there on the chip. But it is very, very fast. So the barrier function looks like this. You can get the group from the item, which tells you it's like the identifier for all of the threads that are in that group. And then you have the group barrier on that group. And everything will stop here until everyone has managed to hit that barrier and passed by it only after them. To use these, once again, you need to use the ND range variant of a parallel for. The logic, again, seeming to be that if you don't ask what your local size should be, then you shouldn't be trying to rely on knowing whether you have or haven't all executed or something. So I kind of get the logic. It does force certain cases on you, but you know, I think it makes an amount of sense. Even if I have personally said, why do we let people do this myself? But I think on balance it does make sense.
Is there like a tag type you can pass to these things instead of a specific number being like something that's fast for this device?
Can you clarify what you mean? Sorry.
Well, so you could pass, instead of saying the group size is 64 or something, which might be quite good for CUDA, you can just say some SYCL object tag type that is something quick for this device that will be selected for you at runtime by the driver. You know, and it might be for your CPU, it might be the SIMD lane width, or for CUDA, it can be, you know 64, 128, something, some multiple of the warp size.
So explicitly saying, I want you to choose the size, but I don't know what it is, because I don't know what the fast size is for this device, but also I need to be able to use the group barrier, essentially.
Yeah.
Like,
I don't really care, but I kind of care. You pick something right, that sort of.
For sure. That's a really, really interesting idea. The short answer is no, you can't do that. The better answer is I think there's probably some value in that.
Yeah,
I
like
don't see why that
SYCL : dealer's choice.
I like it. I like it. It's as good a name as anything else we've covered today, yeah?
It's about as good as range, yeah.
Yeah. Yeah. Again, the people's input on this is welcome, and you can make issues on the repo. Or I've promised I'll get more involved again with the SYCL specification. Put some time aside for it, so I don't see why that couldn't work. Maybe it would need to.
It's also a question of whether the device drivers expose enough information to ask them about these things, which I'm afraid maybe not the case for all kind of devices that SYCL can be used with. So maybe this would be like an optional thing if it existed.
Oh, well, worst case, you just choose 32, right?
Yeah. I mean, the worst case, you choose one.
True, that is very much worst case, but yeah. I
mean, one is guaranteed to work even if the performance sucks, but you have to be choosing this in some way anyway, so it just falls back to what it does currently, surely.
Yeah. Yes. I wonder. I'll try to open up a discussion internally about this, because I have a suspicion that I think a lot about OpenCL in circumstances like this, where it's like, what would OpenCL do? And OpenCL will just let you do this. There's no restriction on calling any of the barrier functions inside the kernel. But I wonder if it has the potential to go wrong. That might be true, and I might not have seen it. So I will try to open a discussion about this. Start off a flame more.
Let me just mention that SYCL does provide device information, so you can ask the queue for its device, and then you can query the device info, and that can give you, for example, the size, the maximum size of the local memory that's available for this device, and the maximum work group size that's available, and several other parameters. So I think from these, perhaps you could also program what you want to achieve.
That's true. That's true. You can certainly ask. There's actually also a query on the kernel, and this isn't like necessarily a perfect number, but there is like a query on the kernel, which is the preferred work group size multiple, and that will give you a number. And if you use that as your work group size, hopefully, according to the implementation, that should be a good enough number. Though again, quality of implementation varies. That's another OpenCLism that has preserved, and I think there are good implementations for the CUDA and HIP backends, but I don't know what they look like in terms of like how they find out what a good size actually is. So yeah. So I'm just making writing down a note about the guessing the local workgroup size and still letting you use the barriers and stuff. Okay, thank you for your patience. So we can see here that when using the local memory in the image convolution sample that we had before, it actually brings the performance, it improves the performance by some way by caching the local values. I imagine what happens 11 by 11 for. It's possible that by the time that we hit this larger convolution width, we're actually using too much local memory and things go wrong again. But certainly for like certain sizes of workgroup problem, we can see that, certain sizes of the problem, we can see that we improve the performance by caching those values by about 20%, which, you know, it's not bad. So are there any further questions about that, about the use of local memory? I guess one thing that I would like to cover is, I mentioned it before, since you asked where it should live, there is this extension which is implemented by oneAPI that has group local memory and group local memory for overwrite. This one's generally the one that you would like to create. This gives you a bunch of entirely uninitialized memory of the whatever size that or whatever shape you pass in, this type name T, whatever thing you pass in here. And we've noticed that this can give you some like really good performance. So for example, here, this is a 64. Wait, is that the right one? Yeah, sorry, yeah, here. It works with auto, so this can look a lot nicer. But this is an array of 64 integers. And the thing that's nice about this is it gives the compiler more information. We've seen some pretty sizable performance impacts from using this. So this is likely to go to the core specification. The accessor is probably going to get deprecated because it puts a bit more information back into the hands of the compiler to let it optimize based on knowing what these shapes are and how it can then start to really do some good transformations. So yeah, this is something to bear in mind as well. I'll drop this link into the chat as well. Yeah. Yeah, so I guess we'd originally said that we would run up until 5, which is where we are now. There are still, I guess in terms of what we ended up looking at, the next bit would be talking about adding local memory tiling to the image convolution sample. I don't really think that we've got. I can hang around for a little bit, but for like the full time to implement this, maybe I'd be happy to answer any other questions that you have, or if you did give it a try and you ran into some trouble, we have a support forum, or you can just email me at. I'll put my email address and links for the support forum in the chat as well if you end up looking at it more. Thank you, and have a nice evening.